Okay, welcome back. Now we're just going to talk a little bit about spectrum analysis and time waveform analysis and introduce the idea of using the log spectrum. Look, we've talked quite a bit about the spectrum in other parts of the course and, in the summary, particularly in the stage 3 bearing faults. The key to it is being organised with your vibration analysis. It's looking at your spectrum and accurately detecting which one is the 1x peak, what is your running speed, and whether you then normalise the graph as I have here, whether you mark off the graph as 1 times running speed, 2 times, 3 times, 4 times, whether you do that or not is totally up to you. The thing is that what really helps you with bearing analysis, and whether you're doing the spectrum of in velocity or acceleration or peak view enveloping any other method, if you can identify your 1x peak to start with, that's going to help you a great deal, because then you can tell which peaks are non-synchronous. Now, just to clarify, non-synchronous means they are non-integer multiples of the running speed of that shaft, the turning speed of the shaft that you're looking at. Whether it's a shaft inside a gearbox or the fan or motor, it doesn't matter. You need to know what the rotating speed is, and therefore you can tell exactly where 4 times running speed and 6 times running speed and 8 times and 7 times and 9 times running speed are. Because bearings cannot generate those frequencies. A bearing cannot generate a frequency at exactly 4.000 times running speed, or 6 times 0.000 times running speed. The frequency will always be a little different to that. It may be, for example, 3.09 times running speed. And you might look at a spectrum and think, well, how can you tell if that's 3 or 3.09? Well, if you normalise the spectrum properly, then you will see that the 3.09 doesn't sit right at 3 times running speed. And if you put your cursor on that peak and you ask for harmonics, if you adjust the harmonics so that you now see a peak at 6.18 and 9. Where am I up to? 27. What did I just say? 24. That's what I'm looking for. 27. That's what I'm. Yeah, I started with 3.09, didn't I? Anyway, you will notice that the harmonics will only line up when you've got a non-synchronous frequency. If it was really 3x, then the second harmonic would be at 6x and the third harmonic would be at 9x instead of being 3.09, 6.18, and what I say, 9.27. They will line up that way, so you can tell. You just have to normalise it properly in the first place. So really, the key to spectrum analysis is just start by auto-normalising your graphs. Make sure the software knows this is 1x, and that way when you see peaks that are non-synchronous, they will stand out. You can put your cursor on it and look for harmonics and see that there are harmonics there. If you don't see them, toggle to log. I'll explain that a bit more in a second, but toggle to log if you're suspicious, and then you'll see, oh, there are some harmonics there. And then you can more easily go looking for sidebands. You can just look in the spectrum yourself and they might stand out pretty clearly, but you can see them. Well, in my sidebands, running speed sidebands, it's an inner race fault. Are they a much lower frequency than that? If they're more like approximately 0.4 times running speed, then that's a fault on the rolling element itself. We've got cage rate sidebands. If there are no sidebands, which is going to be quite common because that's an outer race fault, assuming that the outer race isn't rotating. So we're going to look for non-synchronous frequencies, we're going to look for harmonics, and we're going to look for sidebands. And look, it's kind of convenient that all these rules exist. The fact that they're non-synchronous means we can't confuse them with other things. We're looking for the sidebands. It's all sort of laid out. Now, if you've got a database, well, then you can overlay the frequencies and see if they line up, and that's all good too. Remembering the cautions that I mentioned much earlier on with using the databases and the calculations and so on. Okay, so as I say, the rules are, auto-normalise, look for harmonics, look for sidebands, and that's really the key to using spectrum analysis. And that's whether you're using sort of peak view, enveloping, acceleration spectrum, or velocity spectrum. It's just, the only difference is when you actually see the faults appear in the spectrum. Now, I do want to just mention the benefits of a log display. You can see a linear spectrum down here, and yes, the peaks are quite obvious. But in the log spectrum, we can see signs, very clear signs of the bearing fault, and there may be sidebands in that one as well. Let's just explain how the logarithmic display works. On the one hand, let's say, to use a visual example, that I had the Eiffel Tower. And let's just assume for a minute that 1/10 the size of the Eiffel Tower is a building. And you can just see the building there. And do you see the little tiny dot just to the right of the building? Well, that is a man. And that man is 1/10 the size of the building, just for our example. Okay, so we've got the Eiffel Tower. We've got a building which is the 1/10 the size of the tower. We've got a man that is 1/10 the size of the building, and we've got a mouse that's 1/10 the size of the man. That's a pretty big mouse, actually, but anyway, call it a dog. Anyway, so we've got this situation. Now, if I want to know that that mouse exists, you see, I reckon vibration analysts sort of fall in two camps. Some guys will say, man, if it's a mouse, I don't care. Like if the vibration amplitude's that low, I don't care. But are you the same person that's using enveloping or peak view or anything like that? Well, if you are, sometimes that information's right there in your spectrum. I'm not saying you don't have to use those other techniques, but let's just say that information may be there and you just can't see it. So, the challenge we have is that how do we see the mouse and the man and the building and the tower all on a graph at once? Because to use millimeters per second, for example, I could have a peak, well, hey, I'll use these numbers, although they're obviously very extreme. If I have a peak at 100 millimeters per second, and a peak at 10 millimeters per second, and a peak at 1 millimeter per second, and a peak at 0.1 millimeter per second, how can I see them all on the same graph? You either need to have a computer screen that's this tall and you can see them all, or toggle to log. Because if you toggle to log, look what just happened to my y-axis. Now, the 10x peak, 100 millimeters per second, 10 millimeters per second, 1 millimeter per second, 0.1. They're all evenly spaced down the graph. I can now see my rat, that's a big rat, my man, my building and my tower all on the same scale very easily. So even if I've got a lot of unbalance, which by the way could have caused your bearing fault, but I've got a lot of unbalance, there's my big 1x peak, and I might have a 2x peak which is quite strong, but then I'm seeing peaks which are related to the inner race frequency or the outer race frequency and some side bands. Well, in log, I can see them all. It doesn't matter what their relative amplitude may be, I can see them all. But going to linear, a true linear display, well, how do you scale it so that you can see them? You can't. Now that's in the example, of course, where I've got peaks that are that much different in amplitude. If you're fortunate, see, now you might be even sitting there thinking, well, sometimes I can see those bearing frequencies on my linear graph, and that's all because you probably don't have the Eiffel Tower in your graph. If there's no big unbalance or misalignment peaks, so your scale is lower, you're looking at this situation perhaps. Now you can see all those things all together at the same time. Only when it's convenient that the low vibration is high enough and the high vibration is low enough that you can see it all. But look, most software programs will have one button where you go doink and it toggles over to log and you can look at it and then go doink and toggle back. Now, I can tell you that there's a lot of vibration analysts out there, a lot, that just look at log. And it takes a bit of getting used to, because, you know, you see these peaks and you see a lot of harmonics, and you can think, whoa, look at all those harmonics, I've got looseness. No, you know, if I saw this, you know, harmonic at this frequency, this frequency, this frequency, and this frequency, I could panic and think that it's, you know, a looseness problem. Whereas no, I've got one dominant peak and a bunch of other little peaks. So you do have to recalibrate your mind a little bit, but that doesn't take long. But it's up to you whether you look at log occasionally or look at it as your normal graph of choice. I do recommend that you do look at it, because if you are at all interested in getting an early warning of fault conditions, the log scale will reveal those faults to you. And there's lots and lots of examples where you can see all sorts of different fault conditions, not just bearing fault conditions. You can see things that you just miss otherwise. You just miss. They are there, but the graph scale doesn't allow you to see them. So here we've got, an example again, linear scale. Very hard to see those peaks, but in the log scale I can see them quite clearly, and that's a bearing fault. Again, in the linear scale, I can see this series of peaks, but I can't see anything else. In the log scale, I can see that there are peaks there which relate to a bearing fault, and perhaps other things there as well. So, take full advantage of spectrum analysis by using the log scale. Second thing to comment on, separately we're talking about time waveform analysis, but time waveform analysis is very useful when trying to detect bearing faults. It's very useful when looking at low-speed machines, for starters. Time waveform analysis is useful in a whole lot of areas, but particularly in bearing faults, because I can actually see the impacts. As those rolling elements are rolling along, I can see the impacts occurring. I can see the modulation in the time waveform. I can see all sorts of things. I can see the late stage bearing wear. I can see the early stage bearing wear. I can see a pattern some people call angelfish, and that's just the modulation of the vibration. So definitely set up your time waveform properly and use it as another tool to help you detect the bearing fault and increase your confidence that what you're looking at is in fact a bearing fault. Anyway, there are some tips to do with spectrum analysis and time waveform analysis. I hope they were useful. They are both very useful techniques with detecting bearing faults, and we will separately look at demodulation, peak view, shock pulse and those techniques as well.